Today I'm going to be going over how to do the average atomic mass. Yesterday in your guys' sign notes, you were looking at the different equations that can be used for finding the average atomic mass. So today we're just going to be doing some extra practice on that just to make sure that you really understand how to use these equations. Okay, so for this first problem, it says calculate the elemental atomic mass of Mg if the naturally occurring isotopes are 24 Mg, 25 Mg, and 26 Mg. So we have three isotopes. Their masses and abundances are as follows. Okay, so what we're going to do is, in order to find the average atomic mass, we have to take the mass of each isotope times its corresponding abundance, add all of those up in order to find the average atomic mass. So for this one, and there's two different ways that we can do it. We can convert our percent sign or our percents into decimals to start, or we can just keep the percents as they are and then just divide the whole thing by 100. I personally generally do the divide by 100 just so I know that I'm not messing up moving my decimal place before I start. Okay, so for setting this up, I'm going to take the mass of Mg24, so 23.98504 times the abundance, so 78.70, plus the mass of Mg25, so 24.98584 times the abundance, so 10.13, plus the mass of Mg26, so 25.98259 times the abundance, 11.17. We're going to divide that by 100, and that'll give us our average atomic mass. Now, the important thing to note is that we need to make sure that we're paying attention to order of operations. So when you put it in your calculator, you need to be careful about what you're doing, because if you just put in 23.98504 times the percent, and then you hit plus, and then you hit this number, it's going to add that number to this one and then multiply it times this. Okay, so that is not the correct order of operations. So first we need to multiply these two terms together. Generally, I'll write down what I got. Okay, and then I multiply these two together, write down what I got, multiply these two together, write down what I get. Okay, then add those three, hit the equal sign, and then divide by 100. Okay, so just be very careful, especially with whatever calculator you're using. Now, if you have a fancier calculator, you can take advantage of using parentheses, and it'll do order of operations for you, but just make sure that you're being careful. So when I go through and put this all through the calculator, I should get that the average atomic mass is 24.31 atomic mass units, AMU. For this next one, it says, what is the atomic mass of hafnium if out of every 100 atoms, 5 have a mass of 176, 19 have a mass of 177, 27 have a mass of 178, 14 have a mass of 179, and 35 have a mass of 180. Okay, so notice that they don't give us percentages, but they tell us how many out of a whole that we have of each of the isotopes. Okay, what's nice is they do give our whole out of 100. So basically all of these, in order to figure out the percent, we would take the number divided by the whole. So 5 divided by 100, it's just going to be 5%. So we're going to have 5% of the 176 isotope, 19% of the 177, 27% of the 178, 14% of the 179, and 35% of the 180. Again, I'm going to set this up just how I did it before on the previous one. So I'm going to take the mass of my first isotope, so 176, times it by the percentage, which is 5, plus my mass of my second, 177, times the abundance plus the mass of my third, so 178 times the percent abundance, 27, plus 179 times the percent, and then finally 180 times my 35%, and then divide the whole thing by 100. Okay. Again, I need to do order of operations, so I'll multiply these together, write down what I got, these, and this one. Then add them all together, hit the equal sign, and then divide by 100. And what I should get is 178.55 AMU. So the previous problems all had only one unknown. Some atomic mass calculations have more than one unknown. Since mathematically we can't solve for a single answer if there's only one equation with two unknowns, we need to get rid of one of the unknowns by coming up with a second equation. So, for example, boron has two naturally occurring isotopes, B10 with the mass of 10.013 AMU and B11 with the mass of 11.009 AMU. What is the percent abundance of the heavier isotope? Okay, so our heavier isotope in this case would be B11. All right, so what we need to do is plug the provided isotope masses and the atomic mass of boron from the periodic table into the equation for calculating the atomic mass of boron. So to start, I'm going to write out my equation that I've been using for the previous ones. So I'm going to have the mass of my B10, so 10.013, times the percent of boron 10. Okay, but I don't know what that is, so I'm just going to put a P for percent. Then I'm going to put a subscript of 10, so I know that's the percent of my smaller isotope B10. Okay, plus my other isotope, which has a mass of 11.009. And then again, I don't know the percent, so I'm going to have a P, and then the percent of this would be 11. Okay, and then we're going to divide that by 100. And like it said in the hint, we're going to have to look at the atomic mass of boron in the periodic table in order to determine. So if we go to the periodic table and look at it, we see that the average atomic mass for boron is 10.81. Okay, so like it was saying in the problem, we do have two unknown variables. We have P10 and we have P11, so they're different from each other. So we can't just use this single equation in order to solve for this. Okay, so it states, note that we still have two variables in the equation. Write a second equation that relates these two missing variables. So they give us a hint. If the two natural abundances must add up to 100, what is true about the sum of the two isotope fractions? Okay, so if I was going to write out the two percentages, so I have my percent of boron 10 plus my percent of boron 11 has to equal or total out to 100. Okay, and so because I know that, I can then use that to plug into my equation. All right, so I want to know what the abundance is of the heavier isotope. So I want to have just in this equation, just the P11. So I need to find something or rearrange this equation down here in order to plug in to the P10 so that I only have P11 as my only unknown. Okay, so from this equation down here, I'm going to get P10 by itself. So I'm going to subtract P11 to the other side. So I'll have 100 minus P11. Okay, so this here is equal to P10. So I can plug in this into this equation. So to rewrite my equation, I'm going to have my mass times that equation. So 100 minus P11 plus my mass of P11 times the percent of B11 divided by 100 and equal to 10.81. Okay, so now all I have to do is use algebra in order to solve for my P11. So the first step I'm going to do is I'm going to multiply both sides by 100 so that I get the 100 out of the denominator here. Okay, so I'll have 10.013 times 100 minus P11 plus 11.009 times P11 is equal to 1081. Okay, so my next step is that I need to distribute this into this equation. So my 10.013 is going to multiply by 100, and then I'm going to take this and multiply it by the -1. So whenever I do that, I'm going to get 1001.3 minus 10.013 P11 plus 11.009 P11 is equal to 1081. Okay, so I'm going to subtract over this to get my P11s on their own. I'm going to subtract this over, okay, and then I'm going to combine these two different figures. So the negative 10.013 plus the 11.009, 11p. So I will get 0.996 P11 is equal to 79.7. So then my last step in order to get P11 by itself is I have to divide both sides by the 0.996. So I'm going to get P11 is equal to 80%.